today I'll defend inshallah my master's thesis titled Safe and Agile UAV Navigation in Confined and Tight Spaces via Deep Reinforcement Learning. First, I would like to welcome first my advisor, Dr. Mohammed Maisur, and my committee members, Dr. Rami Ashad and Dr. Hafez Mubarak. So first, the outline of this presentation will go from an introduction to methodology, to results, and ends with conclusion. Regarding my thesis title is UAV Navigation in Tight Spaces. So one main motivation of one chosen motivation or a chosen application of a tight spaces is tunnels and pipes, because tunnels and pipes have the ability have the characteristics of being confined, especially if there are small tunnels, and also has the aerodynamic disturbance affecting the drone, not like than other applications, and also needs agility as well, which we'll come to discuss later. So it gets the two parts of the thesis, safety and agility as well. So for this application for tunnel navigation generally, the most known application for, or most known things used is the crawler, which is like a small mobile robot, which actually works good in many conditions, but has some difficulties depending on the surface of the tunnel you have, especially if you have corrosion inside or debris or so on, and also in high inclination vertical tunnels or so, usually they have small motors due to their power and so on, so they can suffer a bit in this. So drone, because of their geometric freedom, solves both of these problems. It can move freely inside and it goes up and down via hovering, which is good. But the trade-off here is the complexity in control, because now you have varying aerodynamic disturbances, you have other challenges as well. You need a robust controller or a way to control well with all of these changes. So why choosing Agile? Mainly one reason is because usually tunnels in inspections and ventilation and so on are really long, in a long setup. So usually you need at least high speed, not too slow, to finish the tunnel setup for inspection and so fast. But the more critical reason is that studies showed that when the drone moves inside confined tunnels really slowly, this affects the aerodynamic disturbance because its own downwash circulates under it. Downwash is when the drone flies, it has the propeller pushing air down. When it moves slow, this pushed air affects the drone in a bad way. So it needs actually to move fast to get less aerodynamic disturbances. The challenges of this problem is that in our case, we choose a half a meter tunnel, which is really tight compared to the drone. So even small errors compile up together, like we need to make even centimeter errors may affect a lot. As well, also the changing nature of the aerodynamic disturbance inside the tunnel that we can't ignore gives a whole new complexity and challenge to solve it with, while staying safe as well in flight. So in literature review, and especially pipes and ducts, like the small ones, not the big caves or so, the literature is split into different parts. Some of them include aerodynamic disturbance modeling and really focus on it, like doing event cameras and capturing the airflow inside a tunnel. Others focus only on a robot arm that has the drone and tests which part of the tunnel goes well, while others focus on navigation, especially with RL or without RL, with classic controllers or so. But usually when the focus is on navigation and planning, it's mainly, they mainly ignore the aerodynamic disturbance. Only few references get both fully, which one of them is the reference one, which is one of our main references that did a geometric, did a planning via geometry and used aerodynamic disturbance and had small safety margins. Also, safety is not well introduced in the pipes, especially. Only one of the literature found uses CBF. The other uses simpler approaches, which work but have their disadvantages as well. So, seeing the research gap, first, reinforcement learning is not as much explored in this literature, especially it's new. There are 2 or 3 references, but each one either focuses on one area or ignores the safety or the disturbance ones. Also the test of end-to-end RL, which for direct motor RPM, which have been popularized recently by the drone racing scheme, is not tested a lot it's not tested in the tunnel specifically, as well as having the aerodynamic disturbance modeling inside RL frameworks, or generally considering them, and having more tighter safety guarantees, such as barrier states or log barriers or CBF or so, is not well explored or so. So for this thesis contribution, to cover some of the gaps, our first contribution is RL framework for narrow circular tunnels. Second is using direct motor level RPM PPO policy characterization to see what are the effects of using end-to-end RL. Third is including aerodynamic disturbance from a literature, taking the model and embedding it into the RL. Lastly, making a safety guarantees via inner reward as a penalty, not a theoretical guarantee, via log barrier function, but having it adaptive via the aerodynamic disturbance. So, compared to the literature, our work covers circular half-meter tunnel with closed elbow. This is an important part because even in RL literature, they usually leave the space between the segments open, which has its own advantages as well. Uses PPO and direct motor RPM PPO algorithm for RL, integrates the CFD EDL, estimated disturbance level, from the literature into the RL, and finally having the adaptive log barrier reward. For the methodology, to cover the part that we have some parts which are adopted from literature, some parts are adaptation and integration, and others are full. The main two papers are Tayar and Wang. In Tayar, they already made an RL scheme. So the RL baseline of states, actions, reward and transition probability and so on is taken from them to start as a baseline. From the paper of Wang, the main thing is taking the aerodynamic disturbance model, but to analyze this model, I needed to take the quadcopter geometry and tunnel geometry as well, to have the same things that were applied in the CFD and original CFD analysis. Then we go into model adaptation, which are some adaptation. Here is a tunnel and LBO-RDF, quadcopter URDF from the geometry, and the aerodynamic disturbance model integrated to Python to then be used in the RL library. Then, from the observation, so in the paper here worked on a different simulator. We used the simulator done by PyBullet drones. We had two extra factors that needed to be added: full addition of aerodynamic disturbance and high speed too. As the part we talked about agility. So adding high speed and body drag needed more of the original reward, summary reward tuning, and also needed an action filter we'll talk about. Then with the reward tuning and the action filter and the adaptive safety barrier, all of them goes to the RL policy training. For the system overview, more detail, the quadcopter physics starts working from the URDF with the main equations, then feeds into our 20-dimensional observations from the relative position, and quaternion and velocities, then go to the control policy for PPO, which is actor-critic structure with this neural network structure, which then gives an action, which is a percentage of the hover RPM, and then goes to a filter of the EMA filter. Then it's fed into the environment, evaluated via the reward function that has some terms of guidance, stability, and event-based, and has the safety layer of the adaptive log barrier function, which feeds back the feedback from the policy, so the system improves. Then for the system architecture, it has several layers. One of the layers is the physics or simulation layer that feeds to PyBullet, which is the simulator, which is tunnel geometry and elbow and the placement and so on, and their own URDF. Then for the environmental reward layer, we have they call in RL environment for the whole observation, reward, and action scheme, that then gets the aerodynamic disturbance model and the adaptive log barrier fed back as a reward function. Then we have the training layer via the PPO agent and its neural network, normalizing the observation, the reward, and so on. Then we have the monitoring and output layer that logs the data and sees checkpoints and do the callback and so on. For the quadcopter geometry, it was for the geometry itself, size and weight capabilities, it was adapted from Wang to match as well the CFD analysis that was done. Body drag parameters was adapted from different reference, which is UZH Agility, which is a platform similar in size. So we have equivalent body drag parameters with these parameters, which is most important by the math, 1.085, and the overall diameter, which is important here, is about 40 centimeters, the collision diameter. then for the quadrotor dynamics, which were implemented in the URDF, we have the translation dynamics, which includes the thrust and drag force and gravity force. Aptitude dynamics using the quaternions because skipping Euler angles because of its singularities and gimbal lock problems. Going to the rotational dynamics via the inertia and torque. This is the torque calculation in the simulator. And finally, the aerodynamic drag, which is a function of the current RPM and also the drag coefficient as well. For the tunnel geometry, we have a straight 7-meter tunnel segments, which also the geometry is adapted from the same CFD analysis. For the elbow, it's a final 90 degrees elbow, but it's bent with a radius of 0.52. One point to show here is that they were built as small box panels attached together because originally when making them just as a full URDF, the collision geometry wasn't correctly detected in PyBullet assimilator. So it was changed to a box panel structure, whereas as you can see, there are almost small boxes attached here. So the final drone to tunnel size we have is 40 centimeter diameter to a 30 centimeter diameter. So we have here about 5 centimeter distance and 5 centimeter distance. So with a ratio of 1.25. So why choosing RL? First, for a brief about deep reinforcement learning, it is a method as any of the machine learning methods, but instead of having the data labeled via external source or so on, the data is generated by the agent itself by trial and error. So it tries one thing, sees it's good or bad depending on the reward function, then gets the feedback to improve the performance. For the other part, and the most important part actually, the thing that makes RL attractive is that you can include many constraints in RL in the reward function without making the things much more complex. You can almost constrain, as we did, we have some, as you said, guidance and velocity performance parameters, then we can include the aerodynamic disturbance, we can include a safety function and so on. So this is a good advantage, but in return, this makes tuning the reward function more hard and complex to make it fully useful. As we said, also having the ability to include unmodeled behavior via trained models or even a split RL model or so on, and having the ability to do an end-to-end RL for fast controller response and more agility and faster speeds and so on. Then talking about the algorithm used with the reinforcement learning, which is PPO, which stands for Proximal Policy Optimization, in which it's an on-policy algorithm. The thing that is important in on-policy that it's well established in aerial robotics literature because of its stability in training. It doesn't go too far in training and it doesn't use the old corrupted data. It doesn't use a replay buffer, which in simple words mean it just starts fresh and ends the episode and sees, did I do good or bad? If really bad, it's actually discarded and not used at all. So this is the main way, the main advantage of it is the stability in training. It doesn't do as much of unexpected things or so on. And also in hyperparameter sensitivity, as it's on policy, it's not as much hard in tuning the hyperparameter so on because it doesn't affect the replay buffer is not adding on the errors or so on. For the observation, we have a 20-dimensional observation vector going from relative position and relative position to next waypoint, and the direction unit normalized vector of the direction of the next waypoint, quaternion angular velocity and linear velocity, and past action. The thing that's important here is relative position is given to only the next waypoint of the tunnel. The drone in observation doesn't have full coverage. For example, initially it doesn't know the full tunnel segments or the global planet, as we call it. It just knows the next waypoint. This is important in RL for generalization. It never gets its absolute position. It only gets the relative one, which encourages it. And also for the past action, I think it's used for action smoothing. For example, not taking at one episode RPM or at one time step RPM of 100, and then the next episode you take 1,000 or 10,000. Like you're trying to decrease the changes. Then for the action space, as we said, it's in policy given as a between -1 and 1 and calculated as a percentage of the hover RPM, which is a common way used in RL. So this is the weight we try to tune how much we want to include the policy given action into the total hover RPM, whether up or down. In our testing, we went between 0.6 and 0.8. And also the control frequency is 48 Hertz, while the simulator frequency is 240 Hertz for fast physics update. But for control frequency, it's less. To have first given commands or so on, if it was too fast, first it will be the frequency will be too high with the control input, which is not realistic for any controller. And also it needs to be a specific ratio to work directly. So for here we have about 5 time steps. So you need to be in a ratio to do so. And even we tried increasing the control frequency and was worse results. So talking about the structure of a filter, what was happening in the end-to-end RL we had is that the RPM wasn't changing too fast. Like it was going from the 0 to 100 or so too fast, even with the smoothing reward and we talked about and everything, but still it was doing unexpected behavior to reach, it reaches really good performance, but in reality it has unrealistic control input for any hardware. So the goal with making the filter that introduces a bit of lag, but smooths out the signal, which acts like a low-pass filter, which is an exponential moving average filter that has also a weight from the row and the filter to control how much of the filter gain we want as well, which acts as a low-pass filter with a time constant from its calculation about 30 millisecond delay, which is a delay that will need to be studied more in the sim-to-real transfer as well. Then we introduced domain randomization in training. Simply, domain randomization means we have one tunnel setup that, for example, includes one straight in this direction and one straight tunnel in this direction. If we train the drone on only this setup, it will know how to fly really well, but on this setup only. So the goal of domain randomization is in every episode of training, the tunnel setup, it changes randomly. Randomly means we have the elbows and we have the straight segment. So you put a straight segment, then you have a random part that determines the rotation axis of the elbow. So each time phi changes, it changes the position of the lateral and vertical of the elbow, so making an inclination. And also this equation determines the direction of the axis itself. So the drone knows this into the observations and so on. So now we have random setups which need to be included in the way we extract waypoints to be given to the observations. In our case, we chose half meter spacing for half meter waypoint each half meter. Actually, in literature, I didn't find one literature giving a number for this. I tried to have like a middle in between 1 meter and meter in a 7 meter tunnel. In the elbow specifically, it needs to be an arc because it's not a straight line. So it's 5 interior points at an angle between 0 and 90 because the final angle is 90, so they are distributed. So also we need to calculate the sequence, the arc position of the elbows via the junction equation. Actually, the junction equation takes X parameters from the domain randomization. So we randomize here, gives the randomized variables to this equation to calculate the arc position for the elbow, and also the heading direction of the waypoint, which is given in relative position waypoints and so on. So some of the example of 2D random tunnel segments, we tested all of our results between 3 to 6 segments because the time it takes to train on longer segments will take much more time. And I tried actually 8 or 10. The difference in performance wasn't big because anyway, when we reach 6, you pass several ones and so on. So we tested the capabilities of it. Then for the random 3D tunnel segment, this was like totally random. The main conditions is not going to ground or not being underground or so on, but otherwise it's freely via the Rodriguez rotation. Then for the reward function part, the main reward function was adapted actually from the RL baseline literature we said. It consists of nine parameters into 3 categories: guidance, category, stability, and event. For the guidance, the first one is progress. Progress is a reward to encourage the drone to go to the next waypoint. So it's a function of relative distance between the current waypoint and next waypoint and the heading to it, as well with the relative position. Then the center line deviation penalizes the drone when it gets out from the center line of the tunnel. as a function of d, which is distance from center line, normalized by tunnel radius, if we needed to test on different tunnel radius or so on to be normalized as well. Then velocity tracking, it encourages the drone to follow a chosen target velocity. This is a choice with an exponential decay of the velocity error. For stability, orientation, alignment, this tries to have the drone aligned, aligned in U rate and sorry, not U rate, aligned in its axes to be aligned with seeing always going forward in the center line as a function of roll and pitch alignment and U alignment, as it has two parts, which is one of them is the roll and pitch, and one is the U, which are normalized by the factors to increase or decrease them. Then for the angular damping, it's not to make high U rate or pitch and roll rate too fast, changing the angular velocity, because here, if you change too fast, especially in angular, in a small tunnel, you might get crash, and a crash means your total failure. So it's here much more important. Then action smoothness, which we talked about, to smooth the action from the past one if it's too big of a difference. Then for the event ones, we have the waypoint pass, a big reward when it passes the waypoint. Then finish reward, a big waypoint when it ends the whole setup. And the crash penalty, when it totally crashes, so that it's a terminal reward as well, that it crashed, or actually has more details we'll be talking about. Okay, seems for some reason it doesn't. Very good. So the main thing we need to take from the reward function is that it was taken with no drag added, no aerodynamic disturbance added, arguably mostly low speed because of its high weight for the orientation alignment. So when adding drag and high speed of 2 meters per second, it's not actually really high when talking high speed, but we had a range from the CFD analysis of 0 to 3.5 meters per second. So we needed to have a speed we don't pass, so the aerodynamic disturbance stays valid. So the velocity targeting reward and the orientation alignment reward needed tuning and increasing and decreasing ones to let the drone have the ability to pitch, to do specific maneuvers. You need now to pitch for high speed or resisting drag or so on. So it was tuned in this stage. So now let's talk about the log barrier function, which is our safety measure that has different implementation. The centerline deviation reward is a linear function. Means, for example, when the drone is close to the tunnel in 1 centimeter or close in 10 centimeter, it gets the same decrease or increase in the penalty. The difference in a log barrier in a barrier function generally, it penalizes less while you are still far from the boundary. So you don't get penalized if you're now, I have 15 centimeter, I'm too far. If I move a bit, I get low penalty, but then when I'm close to the boundary of 15 centimeter, I get a really, really high boundary, which actually approaches infinity, which is a numerical problem. So replacing the centerline deviation by a normalized log barrier function that has this part is the margin that was there as D, and the D over RD, a margin D max effective is the chosen maximum amount of the barrier to move. For example, the total was 0.25 meter. I chose 0.15 to stay safe as well. So we have the margin. This is actually the log barrier function. But then to normalize it, to have 0 value at the center line exactly, we need to remove this part to add this to normalize it at the end. Also, there's a problem with the log barrier of approaching infinity when it's close to the boundary or almost at the boundary, which numerically destroys the calculation somewhat. So an algorithm in literature called smooth the log barrier had a margin. If this margin or this function gets too low inside, it switches into another small number that keeps the barrier numerically stable. Then for the estimated aerodynamic disturbance we talked about, we have, it's actually a number, a scalar number between 0 and 1, and it's a function of tunnel radius, which in our case was constant, local pitch, tunnel pitch angle, what is the pitch angle of the tunnel, and pass line speed. So actually this was what I was talking about in the beginning. When we're into low speeds, the estimated aerodynamic disturbance is really high compared when we're more high speed, the EDL is 0.25 instead of 0.86. So the motivation came here that now we have aerodynamic disturbance. One solution was to just put it a reward function, not to go there. It's good and it's intuitive, but why not using it for the whole behavior? So instead of using the log barrier with the number chosen that I talked about with 0.15, we're making here this number adaptive, changeable. Depending on the amount of aerodynamic disturbance, it decreases the Dmax efficient, the amount of distance the drone can move through the tunnel itself, with having here max D floor also, because if we get a small number of or a high EDL or so on, to have safety in calculations. So this is the main part of adding the aerodynamic safety. So this GIF shows how the margin changes depending on the EDL level. Depending on the aerodynamic disturbance, the margin either increases or decreases. So the final idea of the adaptive log barrier function is simply replacing the linear centerline deviation with a log barrier function for its more maneuverability outside the center line. The motivation with it for if we need to move agile, we need some time to be outside the center line, we can do maneuvers and so on, but we need to stay safe. So this was the motivation for log barrier function, and adding the aerodynamic disturbance to have it adaptive according to the conditions. Going to the simulation environment, I use PyBullet drones, which is used in literature of RL drones as well. Built the URDF on it, with taking the physics on 240 Hertz as I said, and control frequency of 48 Hertz. Taking the stack of PyBullet drag, it actually, one of its advantages, it has modeling of physics of aerodynamic drag, downwash, and other parts as well. So this was a big advantage. And for training, I'm using a stable baseline 3 RL library. For the training details, I have a 2-layer theme structure for actor and critic and PPO of 256 and 128 individual with an ALU function for the normalization and capturing a specific range, normalizing also the observational reward to get an equivalent values when the units are different, and use CPU-based training, which is a drawback here due to the simulator. So in the final training thing, there is a termination condition and truncation condition. Termination we talked about is the collision one, and when the drone moves excessively, and a truncation when the drone stands in a still position and it times out. It can do this to get reward. The main difference between the two, when termination happens, the calculation in policy as a value function gets 0. So it's not counted, it's a bad behavior anyway, not do. But here in a timeout, you could time out in a space while having the old history as a good one. So why not using it? So you include the value function for it. So for the results, we tested 10 scenarios in our total results. Our total results without drag and with drag and different speeds, adding the EDL barrier and adding as well the without and filter and with filter. So I'll show 4 of the results in the 3D no drag, pure barrier, EDL barrier with no filter, and EDL barrier with a filter. For evaluation metrics as completion rate, mean center line deviation, and mean speed following the speed, also introduced two main RPM matrices to measure how the action was changing. One of them was simultaneous saturation. It is almost a calculation of if the rate of RPM of one motor is at the max and the other one at the lowest. So it measures the percentage this happened, and flip rate, which measures the frequency it changes from the beginning to the end. So for the baseline, we have a training. This is the training progress increase from the beginning. So we had a bad finish rate at the beginning, many time steps, ending with about 80% finish rate of the episode, with a 93% of completion, with following speed was good, about half a meter per second, which was chosen at the beginning of results, and the deviation of 5 centimeters as a mean deviation, showing this results. So as you can see, the drone here is slow. It also, but you will see in the elbow, it tries to keep stable. It will try to be totally aligned when going up, which makes it harder for the drone, especially in low speed. And also, if you zoomed in a bit, you will see that it shakes much more when you're zooming. This will be shown. So it will complete the track, as we said, with the result there. So going from the elbow, from there. So here's the trajectory. It completes, but as you can see, the small shakes here and there, with a mean deviation of 5 centimeters as well. Orientation as well was really, in Neo especially, it was really smooth because it was trying to keep the heading. This only the way it shows how it changes between the vertical segments and horizontal, but it tries to stabilize this. This is the speed following. This is what I was talking about of RPM changes, which is causing the vibrations in the drone. So we had a saturation rate of 67%, flip rate of 99%. For the pure barrier case, in which we have a log barrier function, but that's not adaptive with the 0.15 meter chosen barrier, it was improved, actually trained in training sequence, it improved rapidly, but it took more time in training to reach good performance, or 25 million steps. So the WP percentage is the amount of completion of the same track itself was 91%, with good speed following 1.9. This setup adds the drag and the high speed with the log barrier function, with a deviation of also the same, about 5 centimeters, which is expected because now we give more authority to move in the center line. And here we have the mean estimated disturbance level and the Dmax efficient, which is here constant because it's pure barrier. So for its video, you'll see it was one of the good results here. So it moves faster, it goes between the tunnel, it maneuvers more. There is a small touches of here and there of instability, but compared to other one, it's faster, it goes in elbows, more agile and so on. So here's the trajectory which shows it's better with some center line deviation shown, which is here is actually a good performance criteria. Now we have more changes in the yaw with a peak tilt of between the roll and pitch of 29 degrees and mean speed of 1.89 meter per second, good compared to a target speed of 2 meter per second. The RPM here didn't improve a lot. It improved but a bit, like saturation rate 79, but still 93%. So we still have the same problem. Going to the EDL barrier, having the aerodynamic disturbance to change, but without the filter of the action. We have almost the same, actually it was a worse behavior, which is expected. Now we have an aerodynamic disturbance in the completion rate, especially the speed. The mean speed is higher somewhat at some places. Deviation rate was almost the same, but it was happening more constantly. You can see the video here. So compared to pure barrier, it was a worse result. So here it's more aggressive, even in speed and so on. That's why it's taking turns too aggressively. And here also the deviation appears that it's more changing because of the EDL changing. Here's the peak tilt and speed of 2.2 meter per second, which was talking why it's aggressive here. Also the RPM problem, almost consistent. Then for the EDL area with the EMA filter, here we needed to increase the scale of the action from 0.6 to 0.8 because now we introduce the lag from the filter to get the results. We have almost the same mean deviation generally or close to it, and also but here we'll talk about the saturation rate. The completion rate is almost equivalent. So this is the final model or flagship model, we can call it. So still it's aggressive about the velocity a bit, not as aggressive as the old one. So for trajectory here, it shows more of changes a bit about the center line with a mean deviation, but actually has no mean deviation in this case. Maybe this track didn't lead a lot. And max deviation 6.8 meter per second. The peak tilt is a bit more, but was actually more in the ideal barrier. Speed is overall still higher, but it's not condensed in one area, it's more distributed. So for the RPM, now we have a different look. At least we can see the RPM actions with a saturation of 0.7% and 19% flip rate, compared to other here in the table, talking about starting from 67 or 84% to 0.7% and flip rate of 95 to 90 in the simultaneous saturation level. So the final findings here, the overall model that performs the best is actually the pure barrier case without talking about the filter, which makes sense. But the overall model of adding the filter with the EDL barrier has good compromise between the RPM saturation and the total performance. It doesn't affect performance as much in the lag and so on. So for the conclusion here, The objectives were achieved in terms of making the RL framework, testing the PPO algorithm, and the motor commands as well, having the aerodynamic disturbance model implemented, and the safety aerodynamic disturbance, the adaptive safety function. For limitations and future work, as we took the, first of all, is simulation only. Second part, the EDL weight of aerodynamic disturbance. We tried testing a higher EDL disturbance, about 0.3, 30% increase or decrease, but actually it was worse in the results. So the results that worked is 15% increase or decrease. So it's a bit lower, but for now this one worked, which I'm thinking the reason for it is as we started from a base reward function that had different characteristics and tuned them manually, the reward function needs a whole sweeping and tuning from the beginning to reach better performance in this case, to get more characteristics better and tuned and so on. For future work, extended safety metric logging to get more of the information so we can increase the barrier more or less. Also adding speed modulation depending on the aerodynamic disturbance. Using different simulators for simulator for GPU parallel training because this problem needs much more training to get the full characteristics and so on. And finally, the sim-to-real transfer is a problem that needs investigation. Whether these RPM actions are good enough to test on real hardware drone with the flight response and so on of real flight controllers or not. This will need some investigation. Finally, the technical words ended, which was long. We can talk about acknowledgements, which is the good part. First of all, thanks to Department of Control and Instrumentation Engineering at KFUPM for the opportunity of having the scholarship for my master's, and for the great environment overall of learning and with the faculty for different courses, projects, and going through a different journey that improved me overall. Thanks to IRC for Smart Mobility and Logistics, all the simulations or work there was done on the center's properties. Deepest gratitude and thanks for my advisor, Dr. Mohammed Maisur. Like, we have been from day one of my university, I've been with him. He had been struggling with, like, I have many ideas. I want to go here and there and here. I'm really hard to get on one thing, but he helped me focus, like, see what I really want. Always encouraged me to go to new things and try here and there. So he suffered with me a lot. I took a lot from his time, but really I learned a lot in learning, especially having a weekly meeting, following from day one on a weekly meeting, made me know how to structure even my work. So thanks a lot to him for all his efforts. Also, my sincere thanks to my committee, Dr. Rami Rashad and Dr. Hassan Mubarak. I've been bothering them a lot. They are committee members, but they have been bothered by me a lot. They helped in many stages, seeing every stage of the work, even the proposal, suggesting many new things that were actually right. Getting into technicalities, talking with both of them improved a lot of the work, and even when the time I was hesitant about some of the things to do technically, I always go to their office and they welcome me, so thanks a lot to them. So then, thanks to my family back in Egypt, I wished, of course, to have them here, but they sacrificed a lot of leaving me because I'm the eldest son, so I'm really grateful to them for the opportunity of leaving me to travel, to go where I want, to continue my studies, and they have been really supportive all the way since I was young. Also, to my journey partner here, my wife, she has been with me through that journey, making it much easier, especially in masters. We almost work all the time. We don't have a work hours or so on, so it was sometimes hard, depressed a bit because the results are not good or so. So she was there handling me through different changes and so on. So thanks a lot to her. And for my friends and colleagues, like, I've been lucky since I got here to have many friends. I can't name them one by one because alhamdulillah there are a lot. They've been with me from as well day one, being supportive, being as friends, colleagues, helping in studies, like making me feel this is as a part of my home, because I have many friends, alhamdulillah, here, and they've been supportive. Even today, all of the preparation was, I didn't do many things for the day or even before, so they did all of the things, so thanks a lot to them. Finally, I've been lucky, alhamdulillah, to have been surrounded by supportive people. Since I started here, from every faculty member guiding me, whether in thesis and projects and so on, so thanks a lot to them. And my friends and my family, alhamdulillah, I'm fortunate to have all supportive people around me, so it was a great journey, alhamdulillah. So these are my references. Thank you.
Do you still want to ask questions after the acknowledgement? Just joking. Please go ahead.
You will not pass if you don't ask.
Okay. You had a question earlier. Still?
I think they're afraid not to get pizza if they ask.
Okay, one question at least.
Can you talk more about the frequency of the commands for the controller?
So the thing is, starting from the beginning, it was changing too fast. Some of the solutions were about changing the action smoothness in the reward function. Actually, it was changed a bit, but because the reward function is fully tuned, changing too much corrupts the whole reward function structure. So I wanted a frequency to try to test a time constant for a lag, which is equivalent for a motor time constant in a response, while also having a response closer to real flight controllers in any controller in the frequency of changes. So this reduction was happened, but actually I think still it needs more reduction and more tuning for implementing on a real hardware. So now still the frequency is a bit high. It's less condensed and happens less frequent and so on, but still has high factor, so it needs more tuning still.
Any other questions? Okay, so we thank the audience. If you allow us some time, you can stay outside.